I don't want to do this. Trampolines demonstrate many physics principles such as the change in energy from potential to kinetic and spring potential, as well as the momentum and impulse. We are attempting to measure the impulse of a trampoline on a human being. We measured the mass of our test subject, Rustin Moon, to be 61.05 kilograms, the initial height he began in the first trial to be 162.56 centimeters, or 1.6256 meters. The initial height of the second trial was 237.49 centimeters, or 2.3749 meters. The height that he bounced in the first trial was 54.61 centimeters, or 0.5461 meters. And in the second trial, he bounced 84.45 centimeters, or 0.8445 meters above the trampoline. The equations we used were impulse and linear kinematics. Impulse is equal to the change in momentum, which also equals the mass multiplied by the change in velocity. And we used the third kinematic, where the final velocity squared equals the initial velocity squared plus 2 times the acceleration multiplied by the change in height. As you can see, Rustin is jumping off of a shed onto the trampoline. Notice the change in momentum as he hitched the trampoline. This, my friends, is impulse. Now we will solve for the velocity right before he hits the trampoline and right after he leaves the trampoline. Solving our kinematic equation for velocity, we know that velocity is equal to the square root of 2 times the acceleration times the change in height. Plugging in our known and measured values, we have the square root of 2 times 9.8 meters per second squared times 1.6256 meters, which gives us a velocity of 5.644 meters per second. That is the velocity right before hitting the trampoline. Now to solve for the velocity right after Rustin leaves, we use new measured values. This gives us the square root of 2 times 9.8 meters per second squared times 0.5461 meters. These numbers give us a negative 3.272 meters per second. The negative is directional. He begins moving up, however we chose the positive direction to be down. Now we are solving the momentum of his downward motion before he reaches the trampoline. We plug in his mass and downward velocity to the momentum equation, which gives us a momentum of 344.6 kilogram meters per second. To solve for the momentum as he leaves the trampoline, we plug in his upward velocity to the same equation to get a momentum of negative 199.8 kilogram meters per second. Using the change in momentum, we solve for the total impulse of his bounce. To be negative 544.3 kilogram meters per second. This makes sense because the trampoline changes his direction of motion into the negative direction. It also makes him look as though he is a large bouncing bunny. Our second trial, Rustin leaped above the shed to create a new and higher initial height. We use the same kinematic equation with our new measured values to find his new velocities. We found his downward velocity to be 6.823 meters per second and his upward velocity to be negative 4.071 meters per second. We plugged these values into the momentum equation and found his downward momentum to be 416.5 kilogram meters per second, and his upward momentum after leaving the trampoline to be negative 248.5 kilogram meters per second. Using these values, we found his impulse to be negative 655.1 kilogram meters per second. Trampolines are squishy surfaces similar to some stunt people use to decrease their impulse when jumping off of skyscrapers or other sizable structures. If they were to jump on concrete, they would experience immense pain due to quick change in momentum. Trampolines slow down their descent, leading to a lesser impulse due to a larger time interval in which the momentum changes. Even though trampolines are commonly used for fun, they also demonstrate many different concepts of physics. Just because we are required to have a theme, trampolines make people go up and down just like bunnies do.
Holy crap! If you guys weren't here, I wouldn't have to wear a certain article of clothing.